So welcome back again to the demo part. So we have seen that prime time, that means how to do that timing analysis using prime time, that we have seen. So now after checking that okay, all the things are okay, that means timing information is also okay after post synthesis, then we can go further with the physical design implementation. So physical design implementation means it basically passes through, that means floor planning, then placement, then routing, and finally that means the corresponding layout, auto layout we have to generate. So after generating the layout information, so from there again we have to, that means for back annotated data like this parasitic information, then the corresponding the Verilog file after this doing all these things, and then the corresponding like power information. So this back annotated data again it will be saved from this after that is physical design implementation, then again that data will be fed to the corresponding prime time and see whether the timing information or the power information is meeting or not. That will be done. So once everything is okay, so after then that final layout will be generated, and then that final layout will be, now it will be gone for the, that means it will be sent to the fabrication lab for the final fabrication. Okay, so now we will see that whatever count that means counter we have designed. So now we will see the how to, that means do step by step that auto layout of their counter 16 block. So here we will use that Synopsys another tool which is IC compiler. So IC compiler we will use for our next demo for physical implementation of the counter 16-bit counter. Okay, so the same thing, how to start with this IC compiler. So here you type IC cell minus GUI, so the GUI will start, right? So this is the box at the very beginning. What I have to do, the same thing whenever you open up any Synopsys that means tool, at that time the first thing is that you have to set the link library and the target library. So you have to set that link library. So link library is this one and target library is this one. So you just mention these things in IC compiler here in the command prompt, that okay, this is my link library and this is my target library. You just see that everywhere this is same. Okay, so we are using the typical case everywhere, that means for during the synthesis, during the prime time, then timing analysis, and during the physical design, all the cases we are using the same thing. And here another thing is that we have to set another two things, that is this VSS net that is connected to 0, because we have to give the power supply, like power supply and the ground supply to the chip, right? So this logical 0 net is VSS and logical 1 net is known as VDD. So we have to set in the beginning of that. So how you can set, by this command like set set MW underscore logic 0 to net VSS and set MW logic 1 to VDD. Okay, so again VSS I set, then I need to set this VDD. Okay, so VSS VDD net I have set. So after that what I have to do, I have to create these TLU files. I have to provide the TLU files. So these are the additional files, that means the library information files which is required by the IC compiler. So here you have to set that these TLU files, where you will get this in the technology library itself you will get it. So in the process, then this star RCXT, then TLU plus, here you see this is the max one, and for the minimum TLU choose this cmin TLU plus. Then there is another thing, layer name mapping file between technology library and ITF. So again that will be found in this Astro folder. So in the Astro folder with this tech directory you will find that okay, take to ITF map. Okay, so you just click on this, then choose this. Okay, so for you can do it by that means command line also. So whatever I did in the GUI mode, so there for that this command you have to mention or you have to write. Okay, so after that you have to create the corresponding library. Okay, so library path is where actually we are now, that means we have created that folder for us. So this is the fold path. So the library name, let's consider this library name is test dot w. Okay, w. The technology file is technology file, again you have to get it from this corresponding library. So here you see this is the dot with .tf extension. Okay, and then input reference library is again it will comes under this this one, then processes astro frame, this one. Okay, so okay, and so now I have set all this, that means create this library. So after that what I have to do, that means here this PLU plus file I have set, then this library I have that means set. Now what I have to do, I have to open the, that means what library I have created. So you just do one thing here, you type this command like open so what name I given, that is CNT design, CNT design or something else. The name I have not put right. Okay, just a second. Okay, test.mw. So I have to open that. Right. So after that I have to read the corresponding Verilog file or the netlist file which I have saved. Okay, so the corresponding netlist file is which one? This this one. Okay, so now I have to read that Verilog file. So using this command, so you type here that so whenever you read this Verilog file, this box will come, that means another additional this dialog box will come. So now after that, that means whatever that means cells I have used for counter 16, that means whatever there is a netlist file, so that will come now. So after that what I have to do, I have to do this unify. So you just type this command in here, that unify all these things. So after that what I have to do, I have to link the design between library and this. So again you write this link here. So after that we have to read the corresponding design constant file. Okay, so you just write this, sorry, read, and this count, that file name is CCNT. Okay, so what is that? Okay, so actually it is not linking now. So after that, what you have to do, you have to that means do this floor planning. So how you can do this floor planning? So actually in while you are doing that floor planning, so at that time actually you can see, you can select that okay, you need that flip chip. That means based on the packaging you can select that okay, you need flip chip or any other things you need. So in actually here what you can do, you just create the floor plan. So here this you just write that as okay, core utilization is 6, and from left that is 0.5, from bottom from 0.5, from this 0.5, this 0.5. okay, so that means this is now, this has been placed. Okay, so that means now I have created the floor plan or the box with where my count 16 will be placed, right? So after that what I have to do, so once I create this floor plan, I have to do this, that means this power, that means I have to calculate, that means do this power nets. Okay, so how can I do that? You can just in the pre-route you just click on this, that create rings. For okay, before that you have to write these two command like this derive PG, this derive PG connection, power net is this one, and this one. Okay, so power, with the power net I have just mentioned that okay, that this power net is VDD and 0 is that means connected to 0, that is VSS. Okay, so after that what I have to do, I have to, that means you can, that means you can mention that the corresponding pad name, either you can mention, but here the tool automatically it considers. Okay, so here you see there are like total how many, total 18 pin. So 18 pins are already distributed among this floor planning. So this 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18. So clock reset and another 16 output. So total 18 pairs are, that means input output ports that are already mentioned here. So what is there, that is this one is out 0, this one is out 8, this one is basically out 7. So by default actually the tool itself, it has that means placed those paths. If you want that okay, this is not actually I need, so at that time you can mention. So how you can mention? You can mention the pin name. This is the format for writing the, that means this a TDF file. So here the pin name, then that means the pin, then the pin name with which metal layer you want to basically that means connect with, then along with the height and the width and then height, then at which side it will be placed, whether that is right or left or up, or that means bottom or up, that you have to mention along with the order. That means whether that will be 1, that will be 2, that will be 3, or that will be 4. Okay, so this basically based on this, now you can that means you can specify your corresponding input output file, and you can just import that to IC compiler, so that according to you your corresponding IO pads will be placed. So here actually I am choosing the by default option. So after that what I have to do, I have to go to this create rings. So in the create rings, what you have to do, you have to do this rectangular rings with net VSS and VDD. Okay, so here actually if you write that okay, this is VSS and the corresponding actually the offset will be 0.5 and the width is 1. Okay, with this offset of 0.5 and width of 1. This is also 0.5 and 1. So every one thing is 0.5 and 1. 1 and 0.5. So you can actually that means change this metal layer. So total 9 metal layers are available to you. So you can change any of this metal layer. So I will choose this M6 as metal layer here. So you can choose yours that okay, if you did that will be that means that is totally your choice. But this here you see that whenever I am selecting the left offset and this left segment layer as M6 and then the width is 1, okay, and it is also extended version, and the right is basically also M6, but the bottom and up, okay, then top and bottom they are basically M7 layer, okay, with the same length and same width, but they are on the M7. So that means left and right they are basically on the M6 layer, so along with this extended version, and bottom and up they are basically using M7, right. So M7 with the extended one. So after that this is for VSS, okay. Then again for VDD also I need to do the same thing. So again I need to go to this create rings for VDD. Here actually only the values are different. Here we are using offset as 1.8 and width is 1. So here offset is 1.8 for everything. And the layer is also top and bottom they are M7, and this left and right they are M6, okay. So this is VDD we are now setting. So VDD is also set. So after that we have to create the power strap, okay. So power strap, how you can that means you can go to the power rings, then pre-route, then you create this power straps. So power straps is with the nets, corresponding nets of VDD and VSS. So here actually if you write that okay, the nets is VSS with this corresponding metal layer of M6, and width is basically 3, okay. So this is by default, so with this 3, and this I have to set the corresponding values of this. That means the direction is vertical, that means vertically the straps will be there, that means for VDD and for VSS too, okay. So for VDD is this vertical direction, and that is vertical, and it is with the values of strap at, okay. There are several other options too, okay. I am not touching all those things, so I have done that thing. So for that you see create power strap, direction vertical, net VSS, layer width -3, okay. So that means whatever we are doing in the GUI mode, for that the corresponding command is basically running on the background. So for again I have to create that for VDD too. So VDD, this M6 and all those things are fine with M6 and width of 3. So again correct. So after that what we have to do, we have to that means the power straps we have already done. So after that what we have to do, we have to place it. So how can I place it? You go to this placement cell, then click on this core, that means placement and optimization. Okay, so here you can see that there is several options like effort, medium, high, low, and along with that placement, whether you need power optimization or recovery area or minimize congestions or clock trip for better clock trip synthesis. So what phase you need. So if you need all those, you just click on that, so automatically it will be included in while you are doing the placement cell. Okay, so as this one is a basic one, so I don't have to use these things, but for the advanced that means chip design, you can select like this one. So there is an option, so you don't have to write the comment for it, so you just check on this particular dialog box, so automatically you can, it will be that means included in your comment box, or it will be run in the background. So after that you apply. Okay, so if you just open up this, so these things I have already, after this placement I have already done that. Okay, so so here you see that floor placement with this you can apply, and what is that? So after placement, actually this has been placed. I have done all these things before, so that's why it is not taking. So what we will do, we will just exit this portion, but here actually again if I run this, then we have to change its directory to, or then we are reading the corresponding Verilog file with this. Okay, so after that what we have to do, we have to unify this by running this command. So after that we have to link this, so link, and then we have to read this SDC file. After that, if you do, so it has been read, but what, not open. now it has been read. Then after that what I have to do, I have to go to this create floor plan, and then okay, this is 0.5, this is 0.5, 0.5, 0.5, okay, then we have to create the rings. BSS with 0.5, and this is 1, this is 0.5, 0.5, 0.5, 1, 1, 1, this is metal 6, and this is metal 7. Okay, before that we have to do one thing, that is this one. And then okay, then again for this create rings for VDD, this is offset is 1.8, this is 1.8, this is 1.8, so this is 1.8. okay, so after that, after creating this, so we have to, that means mention the power straps. So how can you write the power straps? That is VSS with metal 6 with the width of 3 and in the vertical direction. Okay, and then again power straps with VDD with the same thing. After that what I have to do, so I have that means created these power straps. Okay, so after that I have to do this placement. So go to this placement, then click on this. Okay, so now you see that my corresponding cell has been placed in between this corresponding whatever area I have chosen. So my design is already placed. Okay, so that means here this is F, that U20, this is F, U15, this is D flip-flop. These are the cells, other cells which I have used in my design. Okay, so after that what I have to do, after that placement I have done. So you can see in each of these, that means things, you can see different, that means report that okay, report placement utilization. So if you want to see, then you can see, that means after placement you can see all this information, or you can save all this information. Again you can go back to this timing analysis and you can do all those things. Okay, but here we will not do that thing. So after placement what we have to do, we have to this place, that means we have to place the clock, as clock is connected with the corresponding registers. So after that what you have to go, you have to go to this clock. So here you select on this clock tree optimization. So there are also some other optimization, that means if you need optimized clock tree synthesis, or if you need area recovery for your design, so that thing you can select. But here just the simple one, whatever is there, so that we will select that. So it will route the corresponding clock in my design. So you see, that means this one is a clock pin. So this one, actually this is the port. So you see this is the port which it is showing at the below, it is showing that okay, this is the clock pin which is connected with this corresponding D flip-flops. Okay, so there are 4 D flip-flops, 1 2 3 4. So with these 4, the clock has been distributed in such a way with this clock tree synthesis. So after that, what we have to do after doing this clock tree synthesis, again you can check all its performance, but after doing that, what I have to do, I have to do this routing throughout this. So you select on this, that core routing and optimization. So here there is this option that whether you need crosstalk reduction during the optimization or other, that means you need crosstalk reduction as well as this signal integrity optimization. So for a 4-bit, this is 4-bit counter basically. So for 4-bit counter, it is not at all required, so that's why we are not, but there are the options where you can select and you can just go on or carry on for your further design. So that will be provided supplementary to this. So once I just placed it, so after that you see that this color is already, that means that has already now routed, that means each of the cell has been now connected, each of the MOS is already connected to each other based on this particular netlist file. Okay, so once I route this, after that you go to this route option, then you can that means you can see several options like this verify route, whether that routing has been done properly or not. So auto route option is also there, global route is option is also there. So if you want to see that okay, that is that means correct or not, so you just select on this, okay, that the routing option is, so here you see that total number of nets 0 are, actually we have not extracted, but this is the report which you are using. So here actually in this dialog box you can see the report. So total vias are like this one. So optimize is 100%, unoptimized is also 100%. So you will get the number of nets is 19. So all that means you'll get the information over here. Okay. So some of the warnings are also there that vias are not connected, so you have to connect those vias manually if it is required. So during this DRC error, if it found that okay, the vias are not connect properly, so at that time you have to do it manually. So after that, what I have to do after that, that means the routing has been done, then we have to do this extract RC. So go to root, then this extract RC. Okay, so extract RC, in the extract RC operation you can that means get all these things, that means so that it gives you all this parasitic information and all those things together. So I need this information and I will use that in prime time. Okay, so this is done, and after that, after extracting the RC, what you can do, that you can write this in this format. You see, actually I have checked it whether that has been already done or not, that we have to check in. Okay, you just write this comment here, that okay, this is cnt extracted.spf with this format of this. If you write this, so here where we are with this, what is that, where is the name, counter cnt extracted, cnt extracted SPF, yes, this one. So you just see actually that SPF file has been already created. So what is that corresponding capacitance and resistance value for each of these which I have used, so that is already mentioned here. Now actually this actually after doing this RC only you will get this, and then again some other things also you can do, which are like this SDF file you have to write. This is standard delay format, that means what are the standard delay format of this. So again you have to write that as this one. So this is delay information I have saved. Then this SDC file also, if you want then you can just do this, and as well as the Verilog file. Okay, so here if I write this, okay, so after that if you see that, okay, this is, where is this CNT extracted, okay, this one. So if you just click on this, this is the, that means after doing the layout this has been created, and before this what was that, that is this one. Okay, so this one is the extracted one, and this one is the that next one is the, that means from the design vision here, and this one is from the that means IC compiler. This one, the other one is from design compiler, and this one is from the IC compiler. So now using this information, this Verilog file and this corresponding SPF file, now you can just give this file to the corresponding prime time to see whether that is running properly or not. So this is for post layout. Okay, so this is for post layout simulation. So here you need to design that. Okay, so this is CNT extracted, the top module name is CNT extracted, CNT underscore extracted. Okay, and design name is this one, the SPF file name is CNT extracted.spf.max, and this SDC file is this one. And if I save it, okay, and then again I need to do what, I need to close this because this is already done. Okay, so discard all, and now if I run this prime time here, and if I execute okay, not this one here, that will be here. So save it, and then you just execute the script of this one. So here you see we are getting the actual data arrival time, though in the earlier it was like 4 point something, but here we are getting slack of 4.51. so that means it has changed a lot. Okay, so that means now again you have to, that means as the slack is too much high, so again you have to start with the design vision, you have to change the clock period, again you have to follow this whole step, and again go back, that means come back to IC compiler, check that, extract all this information, delay information, parasitic information, and the corresponding Verilog file, and again come back. So that's why actually manually, graphically to do this process iteratively, that is very much hectic. So that's why we prefer what, script based language, that means script based technique. So once you run the script, so the script automatically you change only the constant file, so automatically the script will run one by one and you will get it. That means the recursive process will be much more easier to do. Okay, so I think, okay, for this one is the basic simple example of the counter we have seen from top to bottom. That means starting from the HDL code entry to the, that means layout of it, routing, placement, floor plan, everything. So that GDS2 file, it has been, now we have got all this, that means pad cell, we have placed it, we have routed it, everything we did. And after that, what we left, that we have to that means see the corner analysis. Corner analysis means we have to find out the DRC, whether there is any DRC error or not, because as this circuit is still now it is not final, we have to run it some 2-3 iteration. Okay, so that's why this is not final. So after finalizing the circuit, that means when the layout will be finalized, so at that time you have to do this run DRC and extract the RCs. Okay, and after doing that, okay, if DRC and LVS is clean, so at that time you can send it for the fabrication lab for final fabrication. Okay, so this is the total flow of this digital ASIC design. Okay, so with a simple counter we have shown you that how to start with and how to end with, right? And the supplementary materials for advanced version, that means the signal integrity, how to calculate the signal integrity, crosstalk analysis, noise analysis, that part we have left. So because this is to start with, this is to understand first. So after that you can go to the that means complex part. Otherwise actually showing that it will not be that much helpful. So what I am suggesting that I will be providing you to as a supplementary to this course. So once you are familiar with this flow, so that at that time you can go through that and you will be much more, that means knowledgeful by doing that. Okay, so thank you to this code, thank you to this lecture, and I think I hope that you have enjoyed it. Thank you very much and best of luck.